In the summer of 1941, Royal Air Force pilots began dying in alarming numbers over the English Channel. Their Spitfire Mk IVs, the aircraft that had won the Battle of Britain, were being massacred by a new German fighter that could outclimb them, outdive them, and outrun them at altitude. The Focke-Wulf FW-190 appeared without warning and changed everything. British pilots reported the same story. They'd spot the enemy maneuver for position and suddenly find themselves helpless targets. The Spitfire, symbol of British defiance and technological superiority, had become obsolete overnight. Fighter Command was facing a crisis that threatened to hand air superiority back to the Luftwaffe. The solution came not from aerodynamics or weapons or tactics, but from 30 pounds of rotating metal buried inside the Spitfire's nose, a device that would transform the Merlin engine from good to dominant. This is the story of the two-stage supercharger, the engineering breakthrough that saved the Spitfire and changed the air war over Europe. In June 1942, RAF squadron leader Alan Deer, a veteran fighter pilot with 22 confirmed kills, took off in his Spitfire Mk V to intercept German fighters over France. He spotted a formation of FW-190s below him, positioned himself for attack and dove. The Focke-Wulf saw him coming. They didn't run. They climbed, straight up, directly at him. Deer pulled up to maintain his altitude advantage and watched in disbelief through his windscreen. The German fighters were gaining on him. In a climb, the fundamental rule of fighter combat altitude equals energy equals life had been inverted. Deer broke off and ran for home, lucky to escape. This scene repeated itself across the English Channel through 1941 and into 1942. The FW-190, powered by a BMW 801 radial engine, producing one 700 horsepower, dominated the Spitfire Mk V at altitudes above 18,000 feet. British kill-loss ratios, which had favoured the RAF throughout 1940 and early 1941, reversed dramatically. Pilots who had survived the Battle of Britain now found themselves in aircraft that couldn't compete. Fighter Command's leadership knew they faced a technological crisis that demanded an immediate solution. The problem was power. Specifically, power at altitude. Every piston engine loses performance with increasing altitude because air density decreases. Less air means less oxygen for combustion, which means less power. A naturally aspirated engine producing 1,000 horsepower at sea level might generate only 400 horsepower at 20,000 feet. Fighter aircraft operating at high altitude face this fundamental thermodynamic challenge. How do you maintain engine power when there's not enough air? The answer is forced induction, mechanically compressing air before it enters the engine cylinders. Engineers had understood this principle since the 1920s, and by 1940, virtually every high-performance aircraft engine used some form of supercharging. The Rolls-Royce Merlin engine that powered the Spitfire employed a single-stage, single-speed supercharger, a mechanically driven compressor that forced pressurized air into the engine. This system worked well enough to carry the Spitfire through the Battle of Britain, but it had inherent limitations. The supercharger consumed significant engine power to operate, sometimes 150 horsepower, just to drive the compressor. The compressed air also heated up dramatically, which reduced its density and negated some of the pressure increase. The system maintained reasonable power up to about 15,000 feet, then performance fell off rapidly. German engineers working on the BMW 801 had solved these problems differently. Their radial engine used a sophisticated turbocharger system that extracted energy from exhaust gases to drive the compressor, effectively recovering waste heat. The result was an engine that maintained power to much higher altitudes than the Merlin. When the FW-190 entered service in September 1941, it immediately demonstrated superiority over the Spitfire Mk V at combat altitudes. British intelligence initially refused to believe the performance reports, assuming pilots were exaggerating. They weren't. Fighter Command needed a response, and they needed it immediately. Designing a completely new aircraft would take years. Redesigning the Merlin would take months at minimum. The solution came from Rolls-Royce engineers, who had been working on advanced supercharger designs since before the war began. Their answer was conceptually simple but mechanically complex use: 2 supercharger stages, instead of one with an intercooler between them to reduce temperature. The engineering logic was straightforward. A single-stage supercharger compresses air in one step, which generates significant heat and limits the maximum pressure ratio. A 2-stage system compresses the air twice in 2 separate steps, with cooling in between. The first stage compresses incoming air from ambient pressure to an intermediate pressure. That compressed air passes through an intercooler, essentially a radiator for air which removes heat. The second stage then compresses the cooled air to final pressure. This 2-stage compression generates much higher pressure ratios than single-stage systems, while producing less total heat, because each stage does less work, and the intercooler removes heat between stages. The thermodynamic advantages were substantial. The 2-stage supercharger could maintain sea-level pressure in the engine cylinders up to approximately 30,000 feet, double the effective altitude of single-stage systems. Even better, the intercooling between stages meant the compressed air entering the cylinders was much cooler, which increased its density and allowed more air mass per cylinder volume. More air mass meant more fuel could be burned efficiently, which meant more power. On paper, the system promised to boost the Merlin's high-altitude performance by 30 to 40%. But paper calculations are easy. Manufacturing a 2-stage supercharger that would fit inside a Spitfire's engine compartment, survive combat conditions, and actually deliver the promised performance was extraordinarily difficult. Rolls-Royce engineers at their Derby and Crewe facilities worked around the clock through late 1941 and early 1942 to turn theory into hardware. The mechanical challenges were formidable. Each supercharger stage consisted of an impeller, a rotating disc with curved vanes that accelerated air outward, spinning at tremendous speeds inside a precisely machined housing. The impellers had to be manufactured to tolerances measured in thousandths of an inch, perfectly balanced to prevent vibration, and strong enough to survive sustained operation at speeds that generated massive centrifugal forces. The 2-speed gear mechanism that allowed the supercharger to shift between low and high gear ratios had to be reliable enough to function after hours of combat stress, including violent maneuvers that subjected every component to punishing loads. The intercooler presented its own problems. It needed enough surface area to cool the compressed air effectively, but it had to fit within the Spitfire's existing cowling structure without dramatically increasing drag. Rolls-Royce engineers designed a compact intercooler matrix positioned behind the engine, using ram air from the aircraft's forward motion for cooling. The ducting had to be carefully shaped to ensure adequate airflow without creating turbulence that would reduce cooling efficiency or increase drag. Integration with the Merlin's existing systems required hundreds of engineering modifications. The new supercharger assembly was significantly larger and heavier than the single-stage unit, which affected the aircraft's center of gravity. The engine mountings had to be strengthened to handle increased loads. The cooling system required modification because the 2-stage supercharger generated more waste heat. The fuel system needed adjustment because the engine would consume more fuel at high power settings. Oil system capacity increased to handle higher operating temperatures. Every change cascaded into additional changes, requiring careful coordination between Rolls-Royce and Supermarine, the Spitfire's manufacturer. Testing began in early 1942 using modified Merlin 61 engines installed in prototype aircraft. The results exceeded expectations. In level flight at 30,000 feet, the new engine produced nearly 400 horsepower, more than 50% greater than the Merlin 45, powering the Mk V. Rate of climb increased dramatically. Time to 20,000 feet dropped from over 9 minutes to just over 6. Maximum speed at altitude jumped from 368 miles per hour to 408 miles per hour. The 2-stage Merlin didn't just improve the Spitfire's performance, it transformed the aircraft into a different class of fighter. The production version, designated Merlin 61, began reaching operational squadrons in July 1942 installed in the Spitfire Mk IX. Fighter Command initially planned the Mk IX as a stopgap measure, a quick modification to hold the line until a completely new fighter design could enter service. The aircraft was supposed to be built in limited numbers, just enough to counter the immediate FW-190 threat. In reality, the Mk IX would become the most produced Spitfire variant, with over 500 and 600 built. The two-stage Merlin had given the Spitfire a new lease on life that would carry it through to the end of the war. The first combat test came on July 30th, 1942, when 64 Squadron, newly equipped with Mk IXs, engaged FW-190s over France. British pilots finally had an aircraft that could match the German fighters' performance. The Mk IX could climb with the 190 fight at its preferred altitude and engage on equal terms. Within weeks, kill-loss ratios began shifting back in the RAF's favour. Luftwaffe pilots who had grown confident in their superiority suddenly found themselves facing Spitfires that could challenge them at any altitude. The psychological impact was immediate. German fighter tactics, which had become increasingly aggressive over the summer of 1942, grew more cautious. The engineering improvements extended beyond raw performance numbers. The two-stage supercharger's two-speed gearing system allowed pilots to optimize engine performance for different altitudes. At low altitude, the supercharger operated in moderate supercharge mode, the equivalent of low gear, which provided excellent power without excessive boost pressure. Above approximately 19,000 feet, the supercharger automatically shifted to full supercharge mode, high gear, which maintained power at extreme altitudes. This automatic shifting meant pilots didn't need to manage complex engine controls during combat, when attention needed to focus on tactics and survival. The Merlin 61's improved high-altitude performance also solved problems that went beyond fighter versus fighter combat. German reconnaissance aircraft, particularly the high-altitude Junkers Ju-86R, had been operating with near impunity above 40,000 feet, photographing British defensive positions and industrial facilities. Standard Spitfires couldn't reach these altitudes with sufficient performance to intercept. Specially modified Mk IXs equipped with extended wingtips and pressurized cockpits could now reach these extreme altitudes and successfully intercept the reconnaissance aircraft. In September 1942, a modified Mk IX achieved the first successful interception of a Ju-86R at 43,000 feet, an altitude record for operational combat that demonstrated the two-stage supercharger's capabilities. The success of the Merlin 61 in the Spitfire Mk IX drove further development. Rolls-Royce engineers continued refining the two-stage supercharger design, improving efficiency and reducing weight. The Merlin 66, introduced in late 1942, optimized the supercharger for medium-altitude performance, producing maximum power at around 21,000 feet, ideal for the altitudes where most combat actually occurred. The Merlin 70, which appeared in 1943, provided even better high-altitude performance for photo reconnaissance variants. Each version represented incremental improvements to the basic two-stage concept, squeezing additional performance from the same fundamental design. The two-stage supercharger's impact extended far beyond the Spitfire. The same technology transformed the Hawker Hurricane into a capable ground attack aircraft when fitted with the Merlin 61. It powered the de Havilland Mosquito, turning that remarkable aircraft into one of the war's most versatile and successful designs. The Merlin 60 series engines equipped Lancasters and other heavy bombers, giving them better high-altitude performance and improved reliability. The technology that saved the Spitfire became standard across much of Britain's aircraft inventory. American engineers took notice. The Packard Motor Company, which was building Merlin engines under license in the United States, adopted the two-stage supercharger design for the Merlin V1650-7, which powered late-war variants of the North American P-51 Mustang. The combination of the Mustang's aerodynamically efficient airframe with the two-stage Merlin's high-altitude power created what many historians consider the finest fighter aircraft of World War II. The Mustang could escort bombers all the way to Berlin and back, operating at altitudes above 30,000 feet, where it dominated German fighters. This capability fundamentally changed the strategic bombing campaign over Germany, allowing American bombers to strike targets deep in the Reich with acceptable losses. The two-stage supercharger developed to save the Spitfire ended up influencing the entire air war over Europe. The German response to the two-stage Merlin demonstrated how significant the technological advantage had become. Focke-Wulf engineers rushed to develop improved versions of the FW-190 with better high-altitude performance. The FW-190D, introduced in late 1944, replaced the BMW Radial with a Junkers Jumo 213 inline engine equipped with an advanced supercharger system. The aircraft performed well, but it arrived too late and in too few numbers to affect the air war's outcome. Messerschmitt's Bf-109G received a more powerful DB605 engine with improved supercharging, but it still couldn't match the high-altitude performance of late-model Spitfires. The Germans never fully closed the performance gap that the two-stage Merlin had created. Looking at the engineering achievement in retrospect, what Rolls-Royce accomplished was remarkable for both its technical sophistication and its speed of implementation. From the first combat reports of FW-190 superiority in September 1941 to operational deployment of the Merlin 61 in July 1942 took less than 10 months. That timeline included finalizing the design-solving manufacturing challenges, testing prototypes, setting up production lines, manufacturing engines, installing them in airframes, and getting equipped aircraft to operational squadrons. Modern military procurement programs routinely take a decade or more to field new systems. Rolls-Royce did it in less than a year. The achievement was possible because the two-stage supercharger development didn't start from scratch in 1941. Rolls-Royce engineers had been experimenting with multi-stage supercharging since the late 1930s, driven by the recognition that future air combat would occur at increasing altitudes. When the crisis came, they had foundational research and prototype hardware already in development. The wartime urgency provided resources and eliminated bureaucratic obstacles, but the groundwork had been laid years earlier by engineers who anticipated the need before it became critical. The two-stage supercharger also represented a triumph of incremental innovation over revolutionary redesign. Rolls-Royce didn't try to create a completely new engine. They took a proven, reliable design, the Merlin, and enhanced it with better forced induction. This conservative approach minimized risk and accelerated deployment. The basic Merlin architecture remained unchanged. Only the supercharger system was fundamentally new. This meant that existing manufacturing infrastructure could be adapted rather than rebuilt. Mechanics familiar with the Merlin could service the new engines with minimal additional training, and spare parts inventories remained largely compatible. Revolutionary innovation often generates impressive headlines, but incremental improvement wins wars. The impact on pilot confidence was immeasurable. RAF fighter pilots in early 1942 knew they were flying inferior aircraft into combat against an enemy with a significant performance advantage. That knowledge affected morale tactics and willingness to engage. The arrival of the Mk IX reversed this psychological equation. Pilots now had confidence in their equipment. They could accept combat rather than avoid. It could pursue enemies rather than break off, could fight at altitude rather than retreat to lower levels where the Spitfire maintained some advantage. The engineering improvement translated directly into tactical aggression and operational success. Post-war analysis of air combat records shows the Mk IX's impact quantitatively. In the 6 months before the Mk IX entered service, RAF fighter squadrons operating over France averaged kill-loss ratios of approximately 1.21, barely breaking even. In the 6 months after the Mk IX became widely available, those ratios improved to approximately 3:1 in the RAF's favor. Some of this improvement reflected pilot experience and tactical evolution, but the correlation with the Mk IX's deployment is unmistakable. Better engines translated into more enemy aircraft destroyed, and fewer RAF pilots killed. The two-stage supercharger's influence extended into the jet age. The engineering lessons learned, developing high-performance forced induction systems, directly informed the design of early jet engines, which are essentially highly sophisticated compressors. Engineers who worked on the Merlin's supercharger development moved on to jet engine projects after the war, carrying with them knowledge about high-speed compressor aerodynamics materials, science, and thermal management. The path from the Merlin 61 to the Rolls-Royce Avon and IX jet engines was more direct than most realize. The story of the two-stage supercharger offers lessons that remain relevant. First, performance margins matter. The Spitfire Mk V was not a bad aircraft. It had won the Battle of Britain and served effectively for years. But when confronted with an enemy that was even marginally better, good enough became inadequate. In high-stakes competitions, whether military or commercial, small performance advantages compound into decisive superiority. Second, the value of ongoing research and development becomes apparent only during crisis. Rolls-Royce's investment in supercharger research during the late 1930s must have seemed like an expensive luxury when war hadn't yet started, and existing engines performed adequately. That investment paid enormous dividends when crisis demanded immediate solutions. Organizations that maintain research efforts during peacetime have options during wartime. Those that don't are caught flat-footed. Third, integration matters more than individual components. The two-stage supercharger was mechanically impressive, but its success depended on how well it integrated with the Merlin's existing systems and how effectively it could be installed in the Spitfire's airframe. Engineering excellence requires attention to the complete system, not just the most visible innovations. The human cost of the supercharger war bears remembering. Between the FW-190's introduction in September 1941 and the widespread deployment of the Mk IX in autumn 1942, hundreds of RAF pilots died in unequal combat. They went up in aircraft they knew were inferior and fought anyway because that was their duty. The two-stage supercharger gave their successors better odds, but it came too late for those who died learning just how outclassed the Mk V had become. Engineering solutions take time, and time measured in months costs lives measured in hundreds. When you see restored Spitfires at airshows today, their Merlin engines producing that distinctive howl that stirs something primal in anyone who hears it, remember what's happening inside those engines. Air is being compressed, cooled, compressed again, and forced into the cylinders at pressures that would destroy a naturally aspirated engine. That mechanical symphony represents one of the most significant engineering achievements of the war, not the most famous, not the most celebrated, but one that changed the outcome of the air campaign over Europe. The Spitfire's graceful elliptical wings and elegant lines get the attention. Pilots get the glory. But inside the engine compartment, 30 pounds of carefully engineered metal spinning at thousands of revolutions per minute made the difference between victory and defeat. The two-stage two-speed supercharger saved the Spitfire when it faced obsolescence, gave RAF pilots an aircraft that could compete with the best the Luftwaffe could field, and influence fighter design for the remainder of the war and beyond. That's the power of engineering, not dramatic, not glamorous, just physics, thermodynamics, and precise manufacturing turning air into victory. The engineers who designed it never flew combat missions. Most died in obscurity, their names unknown to history. But their work saved lives, won battles, and changed the war. Every Mk IX pilot who returned safely from a mission over occupied Europe owed his survival, at least in part, to those engineers who solved the problem of maintaining power at altitude. The next time someone tells you the Spitfire won the Battle of Britain through pilot courage and aerodynamic beauty, remind them what happened when courage and beauty faced a better performing enemy. Then tell them about 30 pounds of rotating metal that solved the problem, because that's how wars are actually won, not through valor alone, but through the combination of courage and engineering excellence. The Spitfire's beautiful wings may have captured imagination, but its supercharged engine won the fight.